Hi, I would like to continue today's talk on non-pure chance traffic. So I will talk about what is non-pure chance. In fact, most of the queuing system we study so far are with Markov or Poisson arrival or exponential distributed interarrival time. Okay, so in terms of candle rotation, the first major letter is a big M. M stands for Markov, which is the pure chance traffic. So what happened when that is not pure chance? And when it's not pure chance, it's possible to be, example, from a overflow call from a direct route. When direct route is fully occupied, then they would turn into a secondary path, and that arrival into the secondary path are non-pure chance. Okay, so that with that example, we will look at the slide. So the motivation now is where we want to look at the system where it have a non-pure chance arrivals. So that is the motivation. The Hayward approximation, which we're going to introduce, which are simple and relatively accurate methods, okay? And example of non-pure chance is basically, for example, there is no exponential distributed interarrival time, maybe a constant interarrival time. In that case, it's one extreme. The other extreme is the interarrival times come in a burst. So a burst of customer come in a very short time, and then you have a long quiet period, and then another burst come in. Okay, so what is the definition of non-pure chance? Okay, so in fact we look at the number of arrival per average service time. So the average service time is 1/μ. That is average service time. So in terms of number of arrival within that period, and we look at the variance. When that variance we call big V, and when that is not equal to the average number of arrival per average service time, then the case is called non-pure chance. In the case of Poisson arrival, variance is equal to the average. Okay, that is the characteristic of Poisson arrivals. Okay, so let's look at today's agenda. My name is Tim Ko, and we will look at the result of the Hayward approximation. That's a very simple result, which we can list, and then how to use it, and some remarks about what problem you can encounter, and some exercise. Okay, so let's look at the next results. When we look at this Hayward approximation, basically this 2 point is the basic point. Hayward approximation converge non-pure chance traffic to equivalent pure chance traffic, and also adjustment to the number of circuits, and then apply the Erlang loss formula. Okay, because Erlang loss formula is usable for pure chance traffic. For those of you who are interested in looking at Erlang loss system, there's another video of mine which talk about Erlang loss system. Okay, the idea is the non-pure chance system has a similar blocking probability or congestion rate as a Poisson system with adjusted number of traffic intensity, adjusted number of circuit, number of circuit, and therefore you can use the Erlang loss system. The adjustment is done by EZ. Okay, EZ is basically V over M. For Poisson arrival, pure chance traffic, V over M is equal to 1. For the case of non-pure chance, V over M is not equal to 1. In the case of burst arrival, V variance is larger than the M. Okay. In the case of regular or fixed time inter-arrival time, variance is equal to 0. Therefore, Z is very small indeed. Okay. So in that case, we have 3 parameters. We want to define a non-pure chance system: the original number of circuit, original traffic intensity M, and the Z, which is V over M. Okay, so whatever Z value, you can adjust that into a system with pure chance traffic. In that case, Z equal to 1, and the adjusted number of circuit is N over Z, M over Z. Okay, and therefore you can use Erlang loss equation to do it. Okay, let's move forward to the next slide. Is in terms of using the applications, using the equations or the pure chance or Hayward approximation. So this is an example where non-pure chance offer traffic of to N circuit equal to 3, and the average traffic intensity is 6 lane, and number of variance equal to 9, and Z value therefore is 1.5. So using the relationship, we know 3 number of circuits, 6 average traffic intensity M, and Z equal 1.5. That is equivalent to pure chance traffic of 4 fit into 2 circuits, and that the blocking probability of congestion, time congestion, is 62% approximately. Now, if you do not take into consideration of non-pure chance, just using the Erlang loss formula, then it's basically 3 circuit and 6 lane of inputs. And in that case, it's 59%. So you underestimate the congestion if you don't take into account of the variance, which is higher than the mean. Okay, so with that, we go to the final, second last slide, which is the concluding remarks. So what we've done so far is quite simple. It's a Hayward approximation is a simple and accurate method to handle non-pure chance traffic, okay, where the variance is not equal to M. There's a calculation problem because those are the problems we have. And the last remark is the deficiency of Hayward approximation. Is that in general is a real number because variance divided by M. So N over Z is most likely to be a non-integer. Now, if you recall, for those who know how to do the Erlang loss formula, the Erlang loss formula cannot handle a non-integer circuit number. There's only 2 possible approaches to resolve this problem. You take the smaller of the integer. In that case, it's a more conservative estimate, higher blocking probability, or you're using linear interpolation. So example of linear interpolation is if you have the actual calculation of N over Z is equal to 3.5, for example. So you do the calculation or Erlang loss calculation of E3 of A, 3 circuits, E4 of A, 4 circuits, and because the actual circuit calculate number is 3.5, then you have halfway in between those values you calculate from the Erlang loss formula. Okay, the final point is about the usage or deficiency of Hayward approximation. Hayward approximation will give you, very simply, the average of the overflow traffic, which is M time the equivalent blocking probability. And however, it does not contain any other additional informations. And in many cases, when overflow traffic handled by a alternative path, you need, besides the average overflow values, you probably need the variance of the overflow values, okay? And Hayward cannot provide the variance. Now, is there any other method? Yes, you do. If you really want to do it, there is equivalent random method which is able to calculate the average of overflow and the variance of the overflow. But we're not going into any more details on that. And the very final slide is some exercise for you to do in order for you to understand the Hayward approximation. So in this exercise, the question is find the average of the overflow traffic. It's basically M time E, the earning loss formula of with N divided by EZ circuit and M divided by EZ traffic intensity. Okay, with that remarks, I complete today's talk. Thank you.